Hi, my name is Harlan. Welcome to the Machacon Mechanical Engineering channel. Today, I will discuss the second part of vibration analysis, a predictive maintenance tool for condition monitoring. Fast Fourier Transform spectrum analysis, or the FFT analysis. I have here the frequency domain, vibration signal representation. The abscissa is the frequency, and the ordinate is the velocity. And we have here the line in green, which is the amplitude at a certain frequency level. Fast Fourier Transform vibration analysis. The FFT vibration analyzers rely on digital techniques to acquire spectral data. And the vibration signal is sampled, and a mathematical process called FFT algorithm is performed to acquire the sample data and to obtain the signature. A system response can be represented by displacement, velocity, and acceleration amplitudes, both in the time domain and frequency domains. The time domain consists of an amplitude that varies with time, and when the amplitudes are represented in the frequency domain, they are shown as a series sum of sines and cosines. The FFT spectrum measures the amplitude of a vibration signal at various component frequencies. The fast Fourier transform is an effective way of viewing the vibration signal that is very useful for analysis. The signal is broken down into specific amplitudes at various component frequencies. Fourier Transform is a mathematical tool that transforms time domain signals into frequency domain. This is necessary because the frequency components of vibration signals are not visible from the time domain plot. The amplitudes are then plotted over the frequency scale, and the number of component frequencies and the waveform is divided into is referred to as the number of lines of resolution. The resulting plot is called an FFT spectrum. A periodic function of time can be represented by Fourier series as a sum of infinite number of sines and cosines. So we have the velocity as a function of time. We have the first term, a sub o divided by 2, and the second term here is a sub 1, cosine of 2 pi t, small letter t, which is the time, divided by the period, plus a sub 2, cosine 2 pi 2 times time, divided by the period, plus a sub 3, cosine 2 pi 3 times time over the period t, and so on and so forth, plus you start again with b1, sine, see the difference, sine 2 pi t time over the period, and then we have b sub 2, sine 2 pi times 2 over time all over the period, plus b sub 3, sine 2 pi 3 times time over period, plus and so on and so forth. So infinite number of cosines, infinite number of sines. Or it can be expressed in the summation notation, v as a function of time, a sub o over 2, plus summation from n equals 1 to infinity, a sub n cosine 2 pi n frequency times time, b sub n frequency sine 2 pi n frequency times time. Note that the reciprocal of the period, capital T, is a frequency. So the constants can be obtained as follows. So for A sub O over 2, we integrate it. We have frequency times the integral v as a velocity as a function of time times dt. You integrate it from the scale 0 limit until the period. And A sub n can be obtained using 2 times the frequency integral of velocity function of time cosine 2 pi n frequency time times the dt. And B sub n, also using this integral, 2f and integral of velocity as a function of time, sine, and then 2 pi n frequency times time times dt. Limits from 0 to the period t, capital T. And the amplitude here is determined using the Pythagorean theorem. A sub n, the square root of small letter a sub n squared plus b sub n squared. So if you will plot it, the different responses f, 2f, 3f, 4f, 5f into the frequency scale, and we have here a sample how many lines of resolutions. We have 5 lines of resolutions, and we have amplitude, and this one here is A sub O over 2, and this one is the first amplitude, A sub 1 quantity, square root of A sub 1 squared plus B sub 1 squared, and A sub 2 squared plus B sub 2 squared, and so on and so forth. So I have here the R201 oil pump. This is an actual measurement of vibration on a certain equipment, oil pump, and it's a horizontal measurement, and the RPM, the nominal RPM of the machine is 1800, and we have here the spectrum. It shows here the date and the time. Okay, so the actual RPM being measured is 1780 revolutions per minute, or in terms of hertz or cycles per second, which is 29.67 cycles per second. And the vibration measurements, we note a very large amplitude for velocity, which is measured at 0.497 inches per second. And it occurs at this frequency, 3600 cycles per second, which is 2.02 times 1780. So this one is the order. So it occurs at 2 times the RPM of your equipment. So 3600, if you plot it here, this is 20,000 cycles per second, 40,000 cycles per second, and here you will have the various component frequencies. And this one stands out at 497. So what would be the cause of this? So the analysis shows that it occurs at 2.02 orders. The cause of the vibration has been diagnosed as misalignment. And there are 2 types of misalignment: angular misalignment and parallel misalignment. Angular misalignment causes axial vibration and the running speed frequency, or 1 times x. And parallel misalignment produces radial vibration, twice the running speed at 2 times x. You remember, so if you go back here, this one will be 2 times x. So that's why it's parallel misalignment that causing it. So correction has to be done. It has to be realigned using a laser alignment tool. And then after you do the alignment, you have to check it again by taking the vibration measurements, and so that you will be sure that it will also always fall on the ISO standard, or you will see a lot of improvement. Since most misalignment are a combination of angular and parallel, both the radial and the axial measurements 1x and 2x frequencies are both analyzed. So stay tuned for vibration analysis part 3. Thank you for watching.